welcome to the channel where all you got to do is learn about engine balance. So this is a program that I guess it's a spreadsheet, not really a program, that I wrote when we were designing the V-twin for motorcycles Costa Mesa, MCM. I did a previous video on that teardown. I will be doing more. Lots of decisions were made. But basically, we had a couple of configurations of that 90-degree V-twin. We had one with a single pin, one with a split pin. And I went over the balance a little bit, but I'm sure it didn't make a lot of sense. But let me go over, this is the spreadsheet that we used to develop that motor and all the balance shaft systems for it. So these are some of the variables you can input. It doesn't really need the bore, but wrist pin offset is typical to make sure the thrust load is consistent on one side, and you can move the wrist pin offset a little bit to kind of optimize that. It also changes the piston acceleration from the up to down. Connecting rod length, that's super important as well, because the crank pin counterweight makes a sine wave of force, but the piston doesn't move in a sine wave, and it depends on the connecting rod length. So if you put the connecting rod infinitely long, then it will, but you really can't make an infinitely long connecting rod. Crank axis offset, that's very similar to the wrist pin offset, but that's like if you draw a line through the center of the cylinder and the center of the crankshaft rotation, that's how far they're different. This is typically 0 on a modern engine, but some flathead engines, for packaging reasons, they did shift them off quite a bit. I think like a Briggs & Stratton flathead would be off, I don't know, close to an inch. And the flathead Ford as well is pretty far off center. It's in the spreadsheet. I don't really use it, really. But crank throw, that's just basically your stroke divided by 2. Bore, all that really does is calculate the displacement. And then you can put the crankshaft speed in here. Obviously, the higher the number, the higher the loads are. So you can see what kind of loads are in your connecting rod and what kind of imbalance forces you have. And then this is the piston and small end of the connecting rod mass. So this is in ounces. I'm probably going to update this spreadsheet and make that so it does it in grams. And this is your total balance. Some people use 50%, some people use 100%, but I don't think it matters. It's just semantics on what you're considering 50%, what you're considering to be 100%. So don't worry too much about that. This is the crank balance weight. So this is, you could make this 180 degrees or 30 degrees or 90 degrees from the crank pin. If you have a single crank pin, then 180 is a pretty logical choice, but you might want to move that a couple of degrees this way or that way. And then this is to configure the engine, right? This is a 90-degree V-twin. So I'm defining the crank position, 0 is vertical. And then the first cylinder is 45 degrees. So that's counterclockwise 45 degrees. And then if you keep going counterclockwise, you get to 315 degrees. So that's really negative 45 degrees. So it's 90 degrees between them. And you could also add a second crank pin for the piston number 2. This one I'm going to do is a single pin 90 degree. And then these are the balance shafts, right? So the balance shaft, and this doesn't calculate the moment loads from the balance shaft depending on where they're located. This is just taking the vertical and horizontal moment, or vertical and horizontal loads, but you could totally multiply that by the distance from the center line or the center of mass or whatever and get the moment loads as well. This program doesn't do that, or the spreadsheet doesn't do that, but you could totally do it easy enough. So this is the inch ounce. So basically, if it's an ounce, it's 10 inches away, or if it's an inch, it's 10 ounces away, 10 ounces. So you just multiply the mass times the distance, or the, yeah. And then this is the balance or speed. And in this configuration, I have this one going 2 times rotational speed of the engine, and this one going -2 times. So it's a double order. And then this is the position of it phased from 0. So these are all the inputs that you put in. This is all the results. It's got some interesting stuff in here that you probably don't care about. Mean piston speed, yada, yada, yada. Not really part of this endeavor, but it's stuff that was easily calculatable, so I stuck it in there. But basically, let's go and I'll explain how this spreadsheet works. So basically, I'm going to go from the left side of the spreadsheet to the right and explain what each of these columns does. So basically, this is the crank position. So it's 0 degrees, 1 degree, 2 degrees, and it goes all the way down to 720 degrees because it has a 2 times balance shaft, so you have to go at least that far. If you change the crank speed, like you make that 3,000 RPM, then it recalculates the time. So this is how much time it takes to go 1 degree, from 0 to 0.0056 seconds, right? So put that back to 7,000, and this is 2 microseconds. No, 0.2 microseconds. Anyway, a small number to go 1 degree. So, and you can look at the equation in here. It's nothing, right? This is the only input, that is the only input, and then just some math. Then there's, from that position, you can calculate with these numbers here by doing some trigonometry. You can calculate the connecting rod angle, and that's the angle relative to the cylinder. And then this, by using that same angle, or the same equation, and the connecting rod length and the stroke, you can calculate the wrist pin height. So that's basically the distance from the center of the crank to the wrist pin center line. Obviously, you'd have to get the deck height of the motor, you'd have to add your compression height to this number, right? So if it was a 1-inch compression height on the piston, which is from the top of the piston to the center of the wrist pin, then it would be 7.052. So pretty simple. And then this one's essentially this and this are the same. One's for cylinder 1, one's for cylinder 2. Wrist pin height, one's for cylinder 1, one's for cylinder 2. So that's all that's doing so far. It's not that complicated a math. It's just a little bit of trigonometry in here. So then we'll get to this column, which is piston speed. So basically, this is calculus, but kind of a short-winded explanation of calculus. Like basically, your position of your piston, so basically this guy, or spin height, that's your dx, right? And dt is this number here. So if you remember anything from calculus, dx dt is velocity. So change in position relative to time. So change in x versus change in t. So if you look at this, that's exactly what it is. It's like the difference between this guy, which is column D, that one minus that one, over that one minus, or that one minus that one. So it's a pretty simple equation, and then that gives you velocity. And it turns out this is in inches per second. This just converts it, 12 inches in a foot and 60 seconds in a minute. So this is just converts it to feet per minute. So 5,300 feet per minute. And then we do the same thing for acceleration, right? Because the derivative of position is velocity. The derivative of velocity is acceleration. So this is essentially the same equation that we saw before. It's the distance between, or the change in velocity versus the change in time. So And this just carries on all the way down to the bottom. It does explode when you get to the bottom. You see these numbers here are explosions because you have to have a delta. But if you just make the column go farther than you need to and just ignore those answers that are bullshit, you can get the right answer. So now that we have piston acceleration, this just converts it into G's by using the 32.174 feet per second. And then if you take the piston force, because force equals mass times acceleration, that's the mass of the piston and small end of the rod, and some correction factors to get it in pounds force, then that's your piston force. And you'll notice that this piston force is sometimes positive and sometimes negative, right? Depending on if it's going up or it's going down, right? Not a big surprise there. Everybody knows connecting rod sometimes in compression, sometimes in tension, sometimes accelerating, sometimes it's decelerating. This is percentage of stroke. Doesn't really help us out here, but I had to calculate it to do some other stuff probably. I don't remember. This was 25 years ago when I wrote this spreadsheet. So then we take that force, and it's the same for both pistons, but one piston is on a 45-degree angle, the other one's on a negative 45-degree angle, and they're in different locations relative to time. So basically this accounts for that, right? It accounts for the piston, the cylinder location, and converts the forces on that piston to a vertical motion, which is the Z, and a forward aft motion, which is X. So one's a cosine of that and one's a sine of that. And then this is the force on the connecting rod, which you would think it would be the same as the piston force, but the connecting rod's on an angle, so it's not. So there's some math that goes into that. And then force on the connecting rod. The whole purpose of an internal combustion engine is force on the connecting rod makes torque. So inertial forces do the same thing. So you'll see this is converted to torque with this equation. And again, some are positive, some are negative. So far, hopefully you're with me. And then this whole row, or this whole like I through Q, is for the cylinder number 1. And then this one's for cylinder number 2, right? So this is all the exact same math between all of these ones and all of these ones. And then when I get over here, this is the contribution from all of the stuff, right? This is all the vertical contributions from cylinder number 1, cylinder number 2. This is the crank balancer, and then this is the balance shaft or balance shafts. And this is all vertical motion, and this is all horizontal motion. So this is a little bit getting ahead of the game, because if you go over here farther, the same thing happens with the crank balancer, right? That has a certain amount of G's. There's an imbalance force. That's part of the crank weight, and it just converts it to vertical and horizontal motions by using sines and cosines and some proper math. And then we have 2 balance shafts possible. You can always make one of the balance shafts have a 0 mass, and that'll go away. But this is balance shaft 1, this is balance shaft 2. And then this is the combined forces from the balance shafts. So horizontal balance shaft 1 and 2, vertical balance shaft 1 and 2. So when you add all this stuff together, you can make some pretty graphs of it. So there's the piston pin height, and you can see they're offset by 90 degrees because it's a 90-degree V-twin. If this was a 45-degree V-twin, they'd be 45 degrees apart. I'm going to go back over here and remember this number. I'm going to type it in over here, 10.4. And I'm going to make these balance shafts 0. just because it's funner. And then we can look at the z-forces. So this will not have any balance effects, right? The balancer on the crank does something, but the balance shafts don't. So, and remember the explanation, probably poorly worded explanation that I gave when I was tearing down the V-twin, as you can balance out the primary forces, but you can't balance out the secondary forces. Well, I'm going to explain what that means now. So here's the z-forces. So cylinder number 1 is red, cylinder number 2 is green, okay? And they're offset by the, angle of the V. And you note, and then this is the balancer weight, this blue one here, and then this is the balance shaft weight, which is 0. And then if you add all those together, that's the combined, that's your final imbalance with everything attached. And you'll notice that this is a sine wave, but this piston force is not a sine wave at all. And the reason for that is because we have a connecting rod that is a non-infinite length, right? So this is 125 millimeters, 5020-ish. So I'm going to make that 9999999. Big number, right? And then look what our z-forces are. See these guys? They're sine waves now, or very close to sine waves, right? So it doesn't really affect this too much, but we could balance that out better. But it makes that really good. See? Combines really good on horizontal forces, right? So if you had an infinitely long connecting rod, this is why Scotch yoke engines are pretty cool. Now you have a balanced engine. But if we'll go back to our reality here, anybody remember what that was? 5.0197. Yeah. Now our z-forces are kind of 0 here, but our forward and back forces are not 0, right? They're 1,000 pounds, and it's double order. So that's why I was talking about having you can without a balance shaft on 90-degree V-twin, your primary is balanced, but your secondary is not. So you can get rid of the shaking up and down, but the forward back motion, it's still gonna suck, right? 1,000 pounds is a lot. So that's how this program works. Now let's go back to this table and put these fancy numbers in here. 10.4, nothing magic about it. I just poke numbers in until it looked nice. Z-forces, since this is 0, because the balance shafts are not making they're making an up-down motion opposite each other. Don't mind that crashing noise. But it's making all the forward motions are forward in one time and backward the other time. So so if you look at the x-forces, now our combined forces are hovering around 0, right? This one's like 39 pounds, 59 pounds, 64 pounds, right? And we could probably get this a little better if we poked at it a little bit, but every time you change the connecting rod length or the piston pin offset, like if we go back here and make this have a 0.1 wrist pin offset, right? That's moving the wrist pin in the... Now these numbers are getting bigger, and these numbers are getting bigger and looking wonkier, right? So you have to take all this into consideration when you're making decisions. It also changes the combustion, right? It changes the dwell time, and whether it's the dwell time before the combustion's happening or after the combustion's happening, it all kind of needs to be known. So anyway, that's how this program works. I dug this. I found an old 100 megabyte zip disk and saw the program on it, and I drug it out. I had to dust it off, and there was some errors in it that I had to go back and fix. And then I changed a few things here and there to kind of make the wording make more sense. But basically that's how it works. And if you wanted to do any configuration of engine, this is designed to work with the V-twin, right? V2 balance. And this is 2024 because I updated it this year. I believe it's 2024. Sometimes I forget. But I'm planning on taking this thing and expanding it, I'll basically take this same table and make it for each engine. Well, I'm planning on doing this for the V10, so I'll make essentially five of these spreadsheet pages, tabs, and then add all the five together, so I can understand what the balance forces are. And I'll probably add the moments in too, because when you have a V-twin, even though these up-down imbalance forces and the forward-back imbalance forces, this spreadsheet calculates those. The rods and the pistons are like offset a little bit, right? Unless you have a Harley, which they have a fork and blade rod, so there's zero offset. But that gives you a couple as well, right? That this particular engine does not take into consideration. But when you start getting into an inline, 5 or a 4-cylinder or a V10 or whatever, odd fire, all that stuff starts making more of a difference, right? So I will probably take the spreadsheet and update it to a little bit more fanciness, and put the moments in and make it so it works for, you can make it work for an inline engine up to, I can make it into infinity, as long as, well, not infinity, but I can make it up to a V16, I suppose, just by taking the same geometry information and making sure that I have a V-twin, whatever angle it is, and I put all the information in for the first 2 cylinders on the front, and then the next 2 cylinders, and then the next 2 cylinders, and the next 2 cylinders, and keep going. And then those add up. I just have to make sure that I put these bank angles the same. Or you could do it like a VR32, right? A VR6, or a Volkswagen, right? Essentially the bank angles change for each set of cylinders, because the V is on the same angle, but the pistons aren't. So this is a pretty universal method of doing it, starting out with a V-twin. And if it's not a V-twin, you can just make the piston number 2 the same angle, and then make the mass of the piston half, and then you're fine. So you can cheat a lot with this basic architecture program, or spreadsheet, and get to an answer really quick, and kind of have the magnitude of the forces, 60-ish pounds. Again, probably I could optimize this and make it less, but I didn't want these forces to be 0. I wanted them to be a little bit, so you could see. If it was just a straight line, it wouldn't really mean much to you. But anyway, have any questions? Put them in the comments, and if you like this content, please subscribe to the channel. Thanks. Thanks for watching. If you like this content and want more, subscribe, like, and share.